The topic of today's lecture is basic electrical measurements and sensing devices. I want to make sure that everybody is on the same page, so I would like to ask all of you before I continue watching this lecture or during this lecture, you can always stop the recording and review some of your prerequisite materials from your circuit analysis courses. There are tons of information available out there on the World Wide Web, and it's very important for everyone to be familiar with a basic electrical background and knowledge that is required from your prerequisite courses. So I'm going to pretty much give you a summary of what is covered under basic electrical measurements and sensing devices. Again, we're not going to cover advanced topics simply because that's beyond the scope of our class and beyond what we want to learn in this class. So we're going to concentrate on the basics. As you know, most of the basic most of the devices and devices that are used to measure electrical signals there operate on engineering and physical principles. So as such, it's very important to have at least a basic understanding of what's going on. So we're going to pretty much concentrate on those. As you know, the origin of the forces could be very different. I'm also trying to use less PowerPoint presentation and more concentrating on making these presentations and these lectures more interactive. So as such, it's going to be a little bit different in the way it's being presented in comparison to what we've already seen. So there are forces that are of electromagnetic origin. The electromagnetic field is one of those important sources of one of the important origins of the current. Again, it's important for us to concentrate here on certain equations that we'll be using in this for this particular topic for the next lab. We use Lorentz law. Lorentz law relates force, charge, and electric field. The equation is shown here. It is pretty much described here as force in Newton is equal to a charge multiplied by the summation of the electric field plus the velocity of the particle times the magnetic flux intensity. Now, note here that E here is a separate term, so the intensity E exists as a result of other charges than Q. So we want to make sure we include that in this equation, and then we would calculate the force as such. The other important equation that also relate the force to electric current is by means of the second equation that's provided here. It's going to be highlighted right now. F is B multiplied by I multiplied by L, in which B is the magnetic field. Please, it's the magnetic flux density is the same thing as B above. I is the electric current, and L is the conductor length. So if we equate these equations together, we are going to provide a link between an electrical charge and a mechanical density. This should also be magnetic flux density here. I can just correct it right now, and we are okay. All right. The electric current also measured in ampere, which is coulomb per second. So you guys also make sure you get to know that. So then, as you know from your mechanics from engineering mechanics, F is K times X. This applies to a spring of a stiffness of K or a constant of K. Both spring constant and the stiffness would be used here interchangeably. I refer to this K that's provided down here. It's Newton per meter, and X is the displacement in this spring. I have a figure here to show. Here's the figure. Please look above this point. If you have an F sub S, that is the force developed in the spring as a result of displacement X, or displacement could also be measured here as simply F sub X divided by K, which is the stiffness of the K. So what we try to do is we try to relate these equations to be able to calculate K. So we combine these equations. F is Kx and F is BIL. As such, you can see that K sub X would be BIL as shown here. Okay. So from here we can simply measure X as BIL divided by K. Okay. How do we apply this equation? We can solve for I, and as you can see, I would be K divided by BL multiplied by X. That's the equation that we would be using in solving some of the problems. So let's look at take a look at the problem 4-3. 4-3. The problem indicates that we have a basic meter that is designed for B equals Weber per meter square. L is 0.1 meter and K is 1 Newton per meter. That's the stiffness of the spring. We would like to find the deflection when a direct current of 4 ampere flows through the meter. Again, we use FBIL. We use that equation. This is not B sub I, this is actually B. So B would be 1 multiplied by the current here is 4 amp times 4 times L, which is 0.1. That would be 0.4 Newton. We divide that by the stiffness of the spring in the second step. X would be 0.4 divided by 1. That would be 0.4 meter. That would be the deflection when a direct current of 4A flows through the meter. The procedure, the phenomena is also shown as such here. As you can see, there's a current I that goes through here. Again, on one side, it is connected to F sub S as Kx. This is really the primitive ammeter that's shown as such, and B would be the flux of the magnetic field. So that's really the basics of really the bottom line here. Okay, so that short lecture would help us to pretty much solve some of our labs that are lab problems that would be provided to you in the near future. I don't want to release the labs first because it is going to cause much confusion. I want to make sure we cover some of this material before the lab could be released to you. Thank you for your attention. If you have any questions, please email me for more information. Thank you.